Okay, so good morning, everybody. So today we are going to finish the course of arbitrage theory. Okay, so I will do two things. So I will do an example, okay, of a multi-periodic market. Okay, remind that in the previous session, I have focused on the one period binomial that was a complete market and the one period trinomial that was a market that was incomplete. Okay. And from the first, that is the binomial, okay, we are going to build, okay, multi-periodic model. So we are going to see an example. And then, okay, I want to finish dealing in this framework, okay, the problem of American options. I want you to show you today is that in binomial models, okay, to price a contingent claim, that is to price a European option, is not more complicated than to price an American option, even if, okay, a priori, the problem is more complex for American option. Okay, so, but first of all, I want to deal with a numerical example. That is this one. So first of all, I just want to remind you what we have done, okay, in the case of the binomial model for capital T equal to 1. That is the one period binomial model. Okay, so I remind you what we have done. For the binomial model with capital T equal to 1, we are in this situation. Okay, so we have omega two states of nature. Okay, a probability P such that P of WU is strictly positive and P of WT is strictly positive. For the filtration, I don't have the choice. F0 is the trivial. F1 is the biggest, P of omega. Okay, and I can give a name to this one that will be P. And so in this way, this one is 1 minus P. So in this model, I have two assets, okay, the non-risky with S0T at that is given by exponential RT. So at time t equal to 0, it is equal to 1. And at time t equal to 1, it is equal to exponential R. And I add a risky whose dynamic follows the following. Okay, so I start from S. I go with probability toward SU. And with probability 1 minus P to SD. Okay. And we have seen that in this framework, okay, absence of arbitrage opportunity is equivalent to the return of the non-risky asset is strictly greater than the return of the risky one in the worst case and strictly less than the return of the risky asset in the best case, that is U here. Okay. And we have seen in this situation that we have a unique equivalent martingale measure given by Q of WU is equal to exponential R minus D over U minus D, implying that Q of WD is equal to U minus exponential R over U minus D. Okay? So I have this one. Now, suppose that you have a contingent claim. In this situation, okay, a contingent claim is just something that is represented by two possible values at time t equal to 1. Okay, so it's the payoff of the contingent claim here. My random variable, that is F1 measurable here. So if I want to price this one, okay, I can do because I have a complete market. Okay, so any contingent claim is replicable. Okay, and the arbitrage free price in this situation is just the expectation of the actualized payoff. Okay, that is just in this situation Q. Okay, BU plus 1 minus Q BD, where Q is this quantity. Okay, so what is more, it is possible to hedge. So this one solves the pricing question. So in order to hedge, we have seen together that the quantity of risky asset to put in the hedging portfolio between 0 and 1, okay, will be equal to BU at minus BD at over S1, 1, or I can write it this way directly using my notation, over SU minus SD. That is the difference between the final value of the risky asset, okay? And in order to find the quantity of non-risky asset to put in the hedging portfolio, I just have to remind that the value at 0 of my hedging portfolio, its actualized value, okay, may be written as H00 plus H10 time, okay, S over exponential R. It's stupid what I said, okay, so excuse me, it's this one, okay, because I am at time t equal to 0. Okay, so here you have solved the hedging problem. And I can do everything explicitly in this basic model. And the price to pay is that, okay, here I have a very, very basic dynamic, okay, that is not that realistic, okay, and we are going to see how by combining such model, okay, it is possible to obtain dynamics that may be more and more interesting, okay. So I keep this in mind because as you are going to see, we are going to use it, okay, a lot in the following. So what I want to do now, I am in this setting here, okay? So I am in this setting, so just maybe do this, okay, in order to allow you to write. So it's small, okay, but it will be possible to have a look at home on this, write it this way. Okay, so what I have, in fact, here it's an example we have already seen together, okay, at the beginning of the course, okay, that is just a 3 period, okay, 1, 2, 3, a 3 period binomial model. Okay, so I have a 3 period binomial model, okay. In this case, my universe will be omega, that is WD WU to the power 3, okay. I have two assets, the non-risky that fulfill the classical dynamics, exponential RT, okay, that doesn't change here. And then I have the risky asset. And for the risky asset, okay, I use this binomial tree. And what is the meaning of this binomial tree? It means that at any period, between two periods, okay, I can go up or go down with a return that will be U in the best case, so when I grow up, okay, and that will be D when I go down, okay. And the hypothesis I do here in order to simplify the notation is that you see that the U here, D here, U, D, D square, and so on, okay, are the same from one period to another, meaning that in my situation, okay, the return is independent of the choice of two successive dates. Okay. So it should be possible to extend this, okay, to a model where my return depend on the period I am, okay, it should be possible. It's just that I have to introduce notations that I don't want to introduce today, okay, but you can extend, okay, this to the case where I don't have the equality between the returns between two periods. The only thing I have to preserve, okay, if I do this is that, okay, I want a tree that is a recombining tree, meaning that here goes up and goes down, okay, so increase and decrease will give rise to the same thing as decrease and increase. And what is more, okay, I consider that the probability to increase and the probability to decrease, okay, that I call respectively P and 1 minus P, supposing that my P strictly positive and that my 1 minus P is also strictly positive, are the same for each sub period. But as you know, okay, this importance is not that this hypothesis is not that fundamental because we have proved together that the historical probability is not a quantity that I will have to use if I want to price and to age in this kind of model. Okay. So concerning the information filtration. So for F0, I don't have the choice. It's always the trivial sigma algebra, meaning that at the beginning, I have only my information at time t equal to 0. That is typically the value of the non-risk and the risky asset at time t equal to 0. At the end, I know everything, meaning that the last sigma algebra is the biggest one. That is here the power set of omega, omega being finite here. And we have already seen together that the intermediate information filtration, okay, are F1 and F2. And F1 is generated by two sets, A1 and A2. F2 is generated by four sets. And what are these two sets here and these four sets here? But A1 is the set where I know, okay, F1 is the information I have at time t equal, okay? And what is A1? A1 is the set of the triple, okay, the elements in omega, such that the first component is WU. So it means that you know what happened at the first step and you are here at the first step, okay? Because the first component is WU. What is the set A2 by the complementary set? That is, okay, on A2, it means that at time t equal to 1, I am here. Okay, so since I have this kind of model, I know that at time t equal to 1, I will be there or there. And the filtration that allow me to model this situation is this one, the one that is generated by the set for which the first component is WU, and the set for which the first component of my vector is WT. Okay. For the second period, okay, it's the same situation. The only difference is that I have four possibilities. I can increase twice, increase, decrease, decrease, increase, or decrease, decrease. Okay, so I will have a priori four possible situations here, but since I have a recombining tree, I know that these intermediate values are equal in my tree here. Okay. So, and what are these sets? But B1 is the set, okay, explaining that I am here at time t equal to 2. That is, I know that I have increased twice. Okay, here that I have increased one time and then decreased. Then here I have decreased and then increased. And here I have decreased twice. Okay, it's something that I can represent. B's B1, B2, B3, and B4. And I repeat that I have already define these sets, okay, at the beginning of the course when I have given to you an example, okay, after the introduction. So I just want to do a comment on the notation we are going to take here, okay, concerning probabilities and conditional probabilities. So as you know, the choice of the historical probability here is not important in this kind of modeling, okay? The only thing you have to fulfill here is that every state of nature has to have a probability strictly greater than 0. Okay, it's a condition that I have imposed in the beginning of this course that, okay, if I describe in my omega the states of nature, I want that these states of nature are really states of nature. That is, okay, I want them to have a probability strictly positive. Okay. So just a remark concerning the notation here to make it clearer. So if I take A, B, and C belonging to omega, that is, okay, oh, excuse me, not omega here. I want them to be in WD, WU. Okay. If I am interested in the probability P such that W1 is equal to A and W2 is equal to B and W3 is equal to C, okay, I can express using this relation here, I can express this probability, okay, using successive conditional probability, and conditional probability that will allow me to express the probability on the global universe, okay, as, okay, the product of probability concerning what happened for each sub-period, okay? So I can write it this way. I can write it as the probability that W3 is equal to 3 to C given W1 equal to A and W2 equal to B, time the probability that W2 is equal to B given that W1 is equal to A, and the probability that W1 is equal to A. Okay? So it's the classical decomposition, okay, of a probability on a set having 3 components, okay, using conditional probabilities, okay? And in fact, I introduced notations for this probability, okay? So I will denote the probability that W3 is equal to C given W1 is equal to A, W2 is equal to B. I will denote them, okay? Probability of, write it this way, A, B, C. It's a conditional probability, okay? And in the same way, for P of W2 equal to B given W1 equal to A, I will write it as P of B given A, this way. So in the case, I repeat, in the case of historical probability, this decomposition is not necessary to do because I don't mind it. Right? I don't mind this. The only thing I need to impose is that, okay, these two are strictly positive here because, okay, in my model here, the hypothesis I do is that all this one, okay, are equal to what P if C is equal to WU, 1 minus P if C is equal to WD. The same for this one, P if C is equal to, excuse me, if B is equal to WU, and 1 minus P if B is equal to WD. Okay, so I have this, and the same for this probability here. Okay, this one is P if A is equal to WU is equal to 1 minus P if A is equal to WD. So that's why I have here P1 minus P, P1 minus P, P1 minus P, and so on, okay? So I have this way, in fact, I have several conditional probabilities, okay? Mainly, I have 7 conditional probabilities because, okay, this model of size 3 with 3 periods may be seen as a succession of 1, 2, 3, okay, 4, 5, and in fact 6 sub-model, okay, of size 1 because, okay, I have a recombining 3 in this situation, Okay. So I have this conditional probability here, but you will see that what will be interesting here using this convention and what I have written here, okay, in a nutshell, will be to deal with the risk neutral measure, the equivalent martingale measure. I will use also this decomposition to find the equivalent martingale measure in this situation. Okay, so it's just the classical notations, okay, for the 3-period model, okay, based on a succession here of 6, because I have recombining trees, okay, 6 sub-models of size 1. Okay, so I want to price and to age in this framework, okay, and first of all, before to see if I can price and age, I have to study the properties of the model. So I have to deal, okay, with the arbitrage opportunities, okay, because I don't want them in a good model. And also, I want to deal with the fact that the market is complete or not, okay? So let's do the job here. So you will have the lectures note with this slide, okay? So I put this here, it's a little bit small, but it's the best I do, okay? And it's better than what I can do, okay, if it was a lab station using the blackboard, in fact, because I have this at the very least. Okay, so I can say everything here because we have proved together, so I don't remind the name of the proposition, but it's proposition at the beginning of the course that the no arbitrage hypothesis is equivalent to the fact that I don't have local arbitrage, okay? So global arbitrage is equivalent to the fact that I don't have, in fact, local arbitrage opportunities. But what happened here? As I have already remarked, okay, my model here, that is a 3-period model, is just the succession of 6 models of size 1, okay, with 1 period. And I remark that all of these models are what are, in fact, a binomial model, 2 possibility for the state of nature for any submodel of size 1 here, okay? So it implies that if I am interested in the absence of arbitrage opportunity, since I know that global arbitrage is equivalent to local arbitrages, okay, but I just have to check what happened for all these sub-models. So for all the models of size 1 that are used in order to build, okay, my 3-period model. And what I know is that for each 1-period model, I know the condition of absence of arbitrage opportunity. That is, so keep in mind what is this notation. Okay, it means that I have absence of arbitrage opportunity. Okay, so I have no arbitrage opportunities if the return of the non-risky is strictly greater than the return of the risky in the worst case and strictly less than the return of the non-risky of the risky in the best case. Okay, so if I apply this to my modelization here, I remark that for each submodel, the return of the non-risky asset is equal to exponential R. That for each submodel, the return of the risky in the best case is U, because I have here, let's say, SU over S, that is U. For this one, I have SU to the power 3 divided by SU squared, so I obtain U. In the worst case, it's D. because I have SD over S, and here, for example, I have SD to the power 3 over SD squared, that is also D. Okay, so all the returns are the same for these 6 sub-models, okay, implying that, okay, in fact, I can write the no arbitrage condition here. I can write the no arbitrage condition in this model very basically. The no arbitrage here is equivalent to exactly the same condition as the one we have seen for the one period model, because imposing this condition will imply that I will have no local T arbitrage for each submodel of size 1, okay, because, okay, the parameters of all these models are the same, okay? So I have this. So I have a very basic, okay, condition for no arbitrage opportunity, because all the submodel of size 1 here have the same characteristic. So just a remark here. So suppose that I change a little this model, meaning that if I suppose that here, for example, I have a U1 and a D1, meaning that my return depends on the first period. Here, for example, I can have, okay, a return on this model that is U2, D3, here U3, D3, and so on, okay? If I am in the situation where the returns are not identical for each submodel of size 1, instead of having one condition, I will have simply, okay, 6 conditions depending on the rates or the returns for each submodel of size 1. Here, okay, in order to light and to make the notations lighter, okay, I have decided to impose, okay, the same characteristic for this model of size 1, but be careful, okay, if you have a numerical example, you have first to check that, okay, the returns are the same for all these submodel of size 1, okay. If it's the same, but you have a single condition. If it's not the same, you will have 6 conditions, and you will have to summarize these 6 conditions into a single one. Okay. So I have no arbitrage opportunity in the 3-period model, okay, if and only if I have this one. And for any binomial models, okay, that I recombining models such that, okay, any submodels have the same characteristic, we have this unique condition for no arbitrage opportunity, okay, even if I have 4, 5, 6, and so on periods, okay? So I have no arbitrage opportunity. So I know that the set of the equivalent martingale measure is not empty. The set of the equivalent martingale measure is not empty, okay? And if I want to find an equivalent martingale measure, okay, I need to check the martingale condition. So what is the martingale condition in this case? Okay, for all t belonging to 0, 1, 2, okay, then the conditional expectation under Q of the actualized value of the risky asset at time t plus 1 given ft is equal to S1t. Okay? So a priori here, okay, I have for my 3 periods 3 conditions to check, okay? 3 conditions to check in order to have the martingale property, okay? And according to the construction of my model, okay, if I do this, for the first time, I will have 1 condition to check corresponding to this one. In the second condition, this one and this one, that is 2, and here, this one, and this one. So I have, in fact, 6, in fact, 7, but 2 of them are equal, so 6 equations to solve if I want to solve this one, okay? So I will do the job here for t equal to 0. Do it yourself for t equal to 1. And for t equal to 2, this one, I have done the job in the lecture notes. Okay? So do it at home. For this one, you have it in the lectures note, and I will do it here for t equal to 0. So for t equal to 0, what is nice is that, okay, this conditional expectation is just an expectation. So for t equal to 0, my condition is just that the expectation under Q of S1, 1 is equal to S1, 0. Okay? Okay, so I have this. So it's very easy to solve this condition here, okay, because we are exactly in what we have done for the classical binomial model, okay. So what I have if I do the job here, okay, so I have Q WU multiplied by what value of this one for WU, it is SU plus Q WD SD. Okay, so be careful because it's the actualized value. So I have to divide by exponential R here, divide by exponential R has to be equal to the value of this one at time t equal to 0, that is small s. And in fact, okay, I have done the job for the one period binomial model, okay, proving that if I have this condition, keeping the fact that in mind the fact that the sum of these two is equal to 1 here, it implies that Q of WU is equal to exponential R minus D over U minus D, and Q of WD is equal to U minus D exponential of R over U minus D. Okay, so for this submodel of size 1 here, this one, the martingale condition tell me that, okay, Q of WU has to be equal to this quantity, QWD has to be equal to this quantity. Okay, so if I come back to what I have said at the beginning here, okay, if I do the same job here for Q than the one I have done for P, so for the moment, for T equal to 0, okay, I specify this quantity for Q. I have Q of WU and Q of WD. Okay, so if you do the job for T equal to 1, you will have all these conditional probabilities here. So do the job at home to see what happens. And for T equal to 2, I will obtain all these conditional probabilities here for T equal to 2, as I have done in the lectures note. Okay? So it means that for T equal to 0, I obtain this term. For T equal to 1, I obtain this term. For T equal to 2, I obtain this term for Q, and not for P, but for Q. And so at the end, I obtain Q, okay, entirely. So it's something that I can summarize this way. So I have done the job here for T equal to 0. For T equal to 1 and T equal to 2, I will obtain the following. So T equal to 0 tell me that Q WU is equal to exponential R minus D over U minus D that I will denote by small q, and that Q WD is equal to exponential R minus D, excuse me, U minus the expectation for the exponential of R U minus D, that is in fact 1 minus Q. And with my no arbitrage condition, it implies that both of them are strictly positive here. For T equal to 1, what I will obtain? I will obtain, in fact, that all these conditional probabilities here, okay, so I can write here W1, W2 is equal to Q, Q, W1, WD is equal to 1 minus Q for all W1 belongings to WU WD. And if you do the job for T equal to 2, you obtain that Q of W1, W2, W2, WU is equal to Q of W1, W2, WD is equal to 1 minus Q for all W1 and W2 belonging to WD, WU. And what is the meaning of this one? If I come back to the historical description of my model here, for the historical probability, I have P1 minus P, P1 minus P, P1 minus P, and so on, okay? And what I have proved here is that all the characteristics of each submodel of size 1 being equal in my situation here, I will have for the risk neutral probability Q, 1 minus Q, Q, 1 minus Q, and so on for all of them, okay? So once again, a little remark. Here, I obtain this, I repeat, because the U and the D, that is the U, the D, and the exponential R, that are the return of the non-risky asset, the return of the risky in the best, and the return of the risky in the worst cases, okay, are the same for each submodel of size 1. If I don't impose this condition, okay, I will have for my conditional probabilities, okay, something of this form, but where here, okay, the Q will be different for the 6 submodel of size 1, okay? I will have in the same way to solve this kind of system, okay? And then I will obtain, okay, here QWU that is Q1, QWD that is 1 minus Q1, here, okay, Q of WU given W1 or WU that is equal to Q2, and so on, okay? So here, all these Q are equals here, okay? So all the possibility give rise to the same Q because all the characteristics of my models are the same. If I change this characteristic, of course, I will obtain different quantities here, but the principle is exactly the same. Okay, I repeat that it's just to lighten the notation here. Okay, so it means that at the end, I will be able, as I have said, to compute Q of W1, W2, W3 as using my decomposition Q, W1, W2, W3, the conditional probability Q of W3 given W1, W2, Q to multiply by Q, okay, of W2 given W1 multiplied by Q of W1. This way. Okay, so I have all these 3 given by this one. So I have my Q. And what I can remark here is that my Q is unique. Q is unique because, okay, I can decompose it this way. And for each term, I have obtained what I have, solving a system of 2 equations with 2 unknowns, okay? And so I don't have the choice in Q. Q is unique when I have no arbitrage hypothesis. And this uniqueness implies, as we have proved in the theoretical part of the proof, that my market is complete. So my market is complete, okay? So my market is complete. And what can I do? If my market is complete, I can price and I can hedge, okay? So I have a complete market. So So Q is unique. The market is complete. So if I want to price and if I want to hedge, okay, so to price a contingent claim B at in this market, that is something that is F3 measurable. Okay, to price a contingent claim here in this situation. So what I have to do, so to price a contingent claim here, that is something that is F3 measurable. Okay, what I have to do, but the arbitrage free price process, the actualized arbitrage free price process is given by the expectation under Q of my actualized payoff here, that is B at over exponential 3R given FT. So I have this conditional expectation to compute. I have this conditional expectation to compute. And it's not complicated to compute this conditional expectation. It's not complicated because these conditional expectations, okay, will be obtained through the fact that I know all the conditional probabilities related to Q this way. Okay, all of them are given by this one. Okay, so I will be able to compute easily, okay, this kind of conditional expectation because I have all the conditional probabilities related to my probability Q. And what is more, to hedge, but what I have to say to hedge, okay, I said that I know that A T plus 1 minus AT is given by H1 T S1 T plus 1 minus S1 T. Okay, because I know that I have a particular form for the value at time T of a self-financed financial strategy. So it's exactly the relation I have used in the one period model, implying that H1T may be computed this way. Okay, and that, okay, to obtain H0, what I have to find to obtain H0, but that the value at time T of my aging portfolio, so the actualized value at time T of my aging portfolio is equal to H0T multiplied by 1, that is the actualized value of the non-risky asset, plus H1T multiplied by the actualized value of the risky asset. Okay, so if I have this one, I can deduce this one from this because AT is given by the conditional expectation. Okay, so in this model, I can price and age any contingent claim using what we have done in the previous part of the course, the theoretical part of the course, because I have a model that is complete. Okay? So now we are going to do a numerical example, okay, in this situation, okay, with particular value for the parameters of my model, okay, that is for S, for U, for D, okay, and for R, okay, it's what I need to have, okay, U, D, R, and S, okay, and I will see how to do and to do the job to do this, okay. So let's see what happened here. So I am in this situation. It's what I want to do. So I have taken, okay, the previous situation with 3 periods, U that is equal to 1.1, D that is equal to 0.9, and R that is equal to the logarithm of 1 plus 0.05. So first you remark that here you have exponential R that is strictly greater than D and strictly less than U. So you have no arbitrage here, okay? And I know that this implies from what I have done previously that market is complete. Okay, so I have this. What is more, my starting point is 20 for my risky asset. So I have this dynamic for the risky asset. So you have in black here the value of the risky asset at any time, and in red you have its actualized value. Okay, actualized value that is computed this way. Okay, with my R that is equal to this logarithm here. Okay, so in this case, I want to price a European put with K equal to 20 and T is equal to 3. Okay, so my contingent claim here is a put option on the unique risky asset of my model and with a strike that is equal to K. Okay, so I have this one here. And my objective, okay, will be to be able to price and to hedge this contingent claim in my model here. So just have a look on the parameters of the model, okay? And I see that in this situation here, I am able to find the unique equivalent martingale measure, okay? And what it will be. So keep in mind that I will have here Q1 minus Q, Q1 minus Q, and so on. And because from one model to another, that is for this 6 submodel of psi 1 here, this one, this one, this one, this one, this one, and this one, the parameter U, D, and R are the same. So the Q will be the same for all these models, okay? So what I have here, but I know that here, QWU will be equal to Q of W1 WU for any W1 and equal to Q of W1 W2 WU. And this will be equal to, in this particular case, okay, it will be equal to what? So it is exponential R minus D over U minus D, and you obtain in this situation 3/4, okay, implying that Q WD that is equal here to Q W1 WU, WD, excuse me, is equal to Q of W1 W2 WD that is equal to 1/4. So I have my equivalent martingale measure, okay, given by this expression here. So meaning that here for Q, I have 3/4, okay. So the probability to pass from one state of nature to the increasing state of nature is 3/4 for any period, okay, and 1/4 for the decreasing state, in fact, okay. So I have this, okay. So let's continue. So I want to price in this situation. So my contingent claim is this one, okay, is K minus S13 at plus, okay, with my K that is equal to 20. So if I want to price, AT is equal to what? So AT, I know that it is the conditional expectation under the unique equivalent martingale measure of what? Of the actualized value of B given Ft. Okay. In particular, my B is equal to what? It is K minus S13 at plus, okay, divided by S1 S03 at, and I have here, okay, so I can do the computation. K over S03 at, so it's what I have written here, K over S03 at is equal to 17.28 minus S13 plus the actualized value here, because I divide. Okay, so I can do a tree in order to price this contingent claim, that is in order to find, okay, this 80. So what I have for the contingent claim. So here I have a contingent claim that depends only on the final value of my risky assets. Okay, in this model, I can only take 4 values, okay, 4 final values for the risky asset. So I have S13 in this state of nature. So you have here, keep in mind that in red here, in red, you have S1T here. So you have S13 in this case, that is 23, S13 that is this one, S13 that is this one, and this one. Okay, so if I represent the tree for 80, so I will represent it backward. So first, I can represent A3. A3 is very basic to compute because A3 is just B. So to have B, I just have to compute this term in the 4 situation in red here. Okay, so it will be 0 for the first, 0 for the second, and then I will have particular values for these two. So if I do the computation, and you have the detail in the course, okay, so you have 0 for these states here for 23, you have 0 for this one, 18.81, you have for 15.39, okay, you have 1.89, and for this one, you have 4.69. Here, you have A3 that is equal to B. And it's what happened at time t equal to 3. And in fact, my objective, okay, here will be to solve what happened at the previous time. Okay, so I need to find this one, this one, this one. I use the same notation than the one in the lecture's note, okay, to avoid confusion. This one and this one. Okay, so I will have here A2 at time t equal to 2, A1 at time t equal to 1, and A0 at time t equal to 0. Okay, so I have this. And I can easily compute this conditional expectation because keep in mind that according to what I have said previously, so it's here, yeah, in fact, what I have said here, that is, okay, I know what are all the conditional equivalent martingale measure for all these submodels of size 1, okay? This is Q. Q being in my numerical situation equal to 3 over 4. So in fact, what I have to do, I have simply to apply what I have done for the 1 period model here, okay? That is, find that my price is just a convex combination of the payoff function, the actualized payoff function, where the convex coefficients are given by the equivalent martingale measure. And here, okay, for my 6 submodel of size 1, I can apply this formula for Q that is equal to 3 over 4 and 1 minus Q that is equal to 1 over 4 because of the fact that, okay, for my 6 submodels of size 1, I have the same parameters, and so I will have the same conditional probability. So I have a tree this way, okay, with Q1 minus Q, Q1 minus Q, Q1 minus Q, Q1 minus Q, and so on for the 6 submodel of size 1. So at the end, okay, if I do the job here, okay, what I obtain for this tree. So let's see an example. So I can do the computation. What will be 6? 6 will be equal to 3 over 4 times 0 plus 1 over 4 times 0. That is 0. For 5, 3 over 4 times 0 plus 1 over 4 times 1.89. Okay, and in this situation, I will obtain more or less this one. For 4, it will be 3 over 4, this quantity, plus 1 over 4, this one. So I obtain here 2.58. To obtain this one, it will be 3 over 4 times this one, but I know this one, that is 0, plus 1 over 4 times this one, that is 0.47, and so on. Okay, so I write it 3, 2, 1. Okay, that gives me 0.12, 1, and 0.34. So you have here the arbitrage free price process for this put option. Okay. So in general, it's something that you are able to do. So you start from the end, from the payoff function, okay, and then, okay, what you do, is to compute backward, okay, the price process, the arbitrage free price process, okay, using several times the result I know from each submodel of size 1, okay, for each submodel of size 1. And in order to conclude this question here, so the only thing I have to do now is to find what happened for the aging strategy. What happened for the aging strategy? So I am here, okay, and now I will be interested on finding the composition of the aging portfolio for T belongings to 0, 1, 2. Okay. And once again, okay, we are going to have trees, okay, for this quantity, okay. So I will have here, okay, H0, 0, that I will denote. I use the same notation as the one in the lectures note as 6. I have here H10 that I denote also by 6 here. Then I increase, I decrease, okay, and after I will just write numbers. Here you will have H01 WU. It will be equal to 4. You will have H11 WU that I will denote by green 4. Here H01 WD that I will express by red 5. H11 WD, that will be green 5, and then, okay, so I won't write everything, okay, but I will have, okay, this one here, this one, and this one. So here you will have 1, here 2, 3, 4 times t equal to 2, and I have here quantity of non-risky assets when I have increased 2 times. When I have increase and decrease, that will be the same than the one, then when I will decrease and increase, and here I have this one. So if I want to solve this tree, okay, I have to find, okay, these 12 quantities, okay, obtained from, okay, what I know. Okay, so what we are going to do in this situation? In this situation, we are going to mind, okay, how to do in the one period model. In the one period model, I remind you that if I have, okay, the things this way, so if I have a contingent claim that I will write here in its actualized way, so in the one period model, I have BUBD here, I have P, that is just the expectation of the actualized payoff under Q, okay, and we have seen together that in this situation, H0 is equal to something, H10 is given by BU minus BD over, so SU over exponential R minus SD over exponential R. So what is this? It's the difference between the two values, the two actualized value of the payoff of the contingent claim divided by the difference between the two actualized values of the risky asset at time t equal to 1. And I recover this one, okay, using the fact that this is equal to A0 minus H10, and I have here S simply. Okay. Okay, so I have this. And in fact, we are going to use this result, and we are going to apply it for this submarket of size 1, that is this one here, this submarket of size 1, that will give me 1, 1 here, the second submarket of size 1, that will give me this one, the third submarket of size 1, that will give me this one, the fourth, the fifth, and the sixth at the end. Okay, so let's write an example. Okay, I will choose another example than the one I have done in the lectures note. Okay, so you do this once again backward. Okay, you do this once again backward. Okay, so for example, if I want, let's say 2. Okay, what is 2 here? The quantity of risky asset I have to put in my portfolio at time t equal to 2 when I am in this situation here. So it is according to what I have written here, okay, and using the notation of the multi-periodic model, it will be what? It will be A3, that is the payoff, okay, at which point? So if I am here, it means that I have increase and decrease. So I have WU, WD, and I have to take, okay, the difference when I increase and decrease. So I have this. WU, WD, WD here over what? Okay, the difference of the actualized value of the risky asset. Okay, that is 1 S13 WU, WD, WU minus S1, 3, WU, WD, WD. So I have these two A3 here, I obtain from 3 because I have, okay, I have the 3 for A2. I have the 3 for AT here, okay? So you have everything. In particular, the quantity I am interested in here, I have A3, WU, WD, W2, and here I have A3, WD, WU, WD, WD. So it's exactly what I am interested in. So the difference between the A3 I will do in the next slide are difference between these two states of nature, because I am interested in this model in the computation I do, this one, okay? So I obtain here, let's write it, I obtain 0 minus 1.89 divided by what? By the difference between this quantity that I obtained by the difference between this one and this one here. This term minus this one. You have these two. So I have here 80, 81 minus 15, 39. And I obtain in this condition here for the term 2, okay, I obtain minus 0.55. To obtain the quantity of non-risky asset corresponding to this one, okay, but this is equal to what? So it is equal to H02, okay, WU, WD here. That is equal to what? So this quantity here is equal to, but the value of the portfolio at time 2 for WU, WD minus H12, WU, WT, S12, WU, WD. And I have everything because I have A2, WU, WD, okay, from the previous slide. I have this one here. Where is it here? I have here A2, WU, WD, that is given by 5 here. So it is 0.47. So 0.47 here. Minus this term, that is just this one. And S12 WU WT, so S12 WU WD, that is equal to 17.96. And I obtain for this one, okay, I obtain for this one exactly what I want, that is so it is this one. To just have a look. So be careful, because here I have a minus here, and this one is minus 0.0. So I have a plus here. Here I have a plus. So that's why I obtain here, I obtain, okay, 10 point, okay, 35. If I do the computation of this one, okay. So if I continue, so I have done the job here. Okay, you will see that in the lectures note, I have done the job for this one here. And as an exercise, you can do the job for all the others, okay? And I will just give you the answer here concerning how to fill all these ones, okay? So I have this, what I have done here. I erase what I have done for 2. And we'll just write what happened for all the other ones, okay? So I have, for 1, I have 0. Of course, I have 0 because if you take my put option, okay, here and here, the payoff of my put option is 0. So of course I will obtain 1 equal to 0. For 2, I have done the job previously. For 3, you will obtain -1. For 4, you will obtain 2.634. Okay, for 5, you obtain 11.96. And for 6, you obtain 4.94. And for the quantity of non-risky asset, for sure this one will be 0. For the 3, I obtain 17.27. Okay. For 4, I obtain here, excuse me, I have switched the things. Okay, so excuse me. So I have here, it's not what I have here. So it's okay here. So for 4, it's -0.12, -0.34, -0.23. So you have everything in the lectures note here, but to be clear, okay, 4 will be 2.634, 5 will be 1.96, okay, and 6 will be 4.94. Okay, so you have here, okay, the exact composition of the hedging portfolio in this situation. Okay, and as you have to keep in mind as the philosophy of the approach we have done is that starting from the end, okay, I use several times, that is for any sub-model of size 1, the result, okay, we have for the binomial model, okay, with 1 period, to starting from the end and to go back to the beginning. Okay, so it's not more complicated than this one. Just the last remark I will do is that be careful, because in the examples we have seen together here, the U and the D are, and the exponential R are the same for all the sub-model of size 1. If I change this, it changed nothing to my methodology. It's just that, okay, in order to compute conditional expectation under Q, okay, I will have convex combination, but convex combination that will depend on the third model I work with. Okay, so it's the only difference you have. Okay, so here you have an example of what happened in the case of a put. Okay, and in fact you can have this for any type of contingent claims. Okay, so here a put is something that is path independent, in the sense that, okay, the payoff only depend on the final value. If you have a product with a payoff that depend on the whole trajectory of the asset, for example, okay, an option on maximum or an option on mean, okay, the same methodology apply. You just have to write the payoff at the end, okay, and do to the job, okay, starting from the end to the beginning, okay? So I think that I will stop this video here, okay, and I will finish the course in another video dealing with American option, okay? So see you in the next video.